Our next speaker is Guannan from Purdue University. And Guannan is about to start a postdoc at Tufts, I believe.
As a professor.
As professor, yeah. Even better. So Guannan's about to start at Tufts next year. So, and Guannan's going to talk about contracts for contracts, consolidating smart contracts with behavioral contracts. Thank you.
Yes, thank you, Steve. So good afternoon, everyone. My name is Guannan, and today I'm going to talk about work about contracts for contracts. It's a fancy title, but our paper is actually titled Consolidating Smart Contracts with Behavioral Contracts. And this is joint work with Zhang, Wuqi, Yongwei, and Zhang. So let's start with what is really smart contracts. So they're contracts in the sense that they specify some form of assumption and guarantees, but between business parties about some transactions, right? But smart contracts, they're also programs in the sense that they're autonomous programs signed and stored on a blockchain. And the blockchain mechanism will ensure that this agreement will be eventually realized among our business parties. In this sense, they are sort of smart programs, right? And there are a lot of different smart contract program languages and blockchain platforms. And one of the most popular one is called Solidity, and it's running on the Ethereum blockchain. And this pie chart shows the kind of basically the market share among different blockchain, and you can see the blue pie is the total value locked on the Ethereum blockchain. So it's basically really the majority blockchain, and Solidity is the program language to write smart contract programs running on Ethereum. And as a program language, the programs in Solidity will be compiled to a bytecode running on the Ethereum virtual machine and in a decentralized way, right? But just as all programs, they have bugs, but in the setting of smart contracts and blockchain, those bugs can be attacked and can be exploited and causing real money loss, right? And the table here, which is I get a screenshot from a study at ICSI last year, which is also authored by one of the co-authors of this paper. They just list several attacks, and you can see the total amount of fund loss is over, I think, 200 million US dollars. That's really a lot of money. And one of the reasons that those programs can be attacked is because of the lack of clearly specified safety conditions. So programmers sometimes just omitted those conditions because of overlook somehow. But as PR researchers, we sometimes blame the language because the language does not provide enough mechanisms for programmers to specify and enforce those safety conditions. And interestingly, in the research community, there's also a notion called behavioral contracts. And this is a kind of metaphor, and it also specifies assumptions and guarantees between software components. And those behavioral contracts, they are sort of specifications. And those assumptions, you can think of they are preconditions, and guarantees are postconditions. And in a language with behavioral contract support, programmers can write down those assumptions or guarantees in the same program language as a host program language. So this is very convenient to use and easy to learn for programmers. And those conditions will be monitored at runtime if there's any violations. And this will further help with maintenance or debugging of the program. So the idea of our paper is to think about there are two similar notions that are both called sort of contracts, but for different entities. And what if we can apply the design by contract approach to smart contracts, right? And more precisely, in this work, we propose Console, which is both an extension to the Solidity language and also a transpiler that supports behavioral contracts for this popular smart contract program language. And we can annotate rich precondition and postconditions to Solidity programs, and those conditions will be monitored for any violation at runtime. So this Console as a transpiler to translate the program to implement this. And this will improve readability and maintainability, and potentially, because we have a more convenient way to specify those conditions, this potentially could further help with fuzzing or static verification, etc. Right? So let's look at example. How it looks like, right? So this is a function called getPrice, and it's kind of getting the price from an input value of this chain link, and it's calling a function over this chain link, get latest run data, and return this rate from the oracle with the ETH Ethereum price, and eventually the programmer can call this getPrice function, right? But the programmer also want to ensure that whatever the price is returned by this function is bounded by a fluctuation, like this 95% or 1.05%, right? This is a post condition, and the programmer can just write down a little bit more annotation on top of the actual function to use this ensures keywords to write down the post condition. And this will be just checked at runtime when calling this function, right? So this is really all straightforward and simple to implement. This is not really much different from assertions. But now if we look at this function, there is an argument, which is an address argument called chainlink. What if we want to say something about the argument chainlink, right? And here the argument is an address. It's kind of like a little bit special data type in Solidity. And it's basically integer. It's like pointers or references in ordinary program languages, but it's 160-bit integers. And it's also first-class values. You can pass it around, storing into other data structures. That's all okay. But as addresses, they represent other instances of contracts or users so that you can interact with other contracts and users to make transactions or transfer monies, right? So they contain those callable functions. Like here, we're calling this latest run data on chainlink, right? Because this chainlink is an argument to getPrice, we may think about we can add a precondition to getPrice to say something about what chainlink should behave, right? But this is not really an easy job to do because when we are calling this getPrice function, even though we zone this argument, but we do not know the potential argument when calling this address, right? We do not really know what's our actual argument potentially taken by the chainlink and what's the return value of this ETH price when calling this getPrice, right? So we cannot really call this because this is kind of like a similar higher order essence here, right? So this is a unique feature supported by Console to express and monitoring those conditions for addresses and their latent costs. And our idea is not really entirely new thing because we borrow ideas from previous research in functional programming community and this paper from Bob Findler and Matthias Felisen about contracts for higher order functions because we found the problem is quite similar, but there are already quite good solutions in functional programming community. But of course, we need to tailor the solution to the setting of Solidity and smart contracts. And the basic idea in this paper is really to delay the check of those behaviors of higher order functions, especially when functions are used as values of other functions or return from other functions. Right. Before I'm going to talk about the actual mechanisms, we can revisit this function and look at the example here and how the actual specification looks like. Right. Here are two additional require statements. This is actually, we simplified from a real world smart contract programs. And there are two requirement statements to check the updated time and also the return price for certain security reason. And we don't really have to annotate those things here. We can just also write all the specification along in the single place using this where clause, and we can add a little bit of signature about the chainlink and the latest run data, what it returns, what are those binding names we need to use, and we use the same syntax to ensure whatever the post condition already annotated here, right? So this is the post condition, and we can basically remove those two conditions from the function body. And the checks will be preserved whenever this chainlink is passed around in the function body or when it's called multiple times. And all those checks will be preserved and actually performed, ensured by our compilation schema. Right. So this is really good for decoupling, especially repeated low-level checks from business logic. But now the problem is we need to know when to perform those checks of addresses cost, because the trouble again here is those addresses, they're first-class values, and they can flow around, right? And the basic idea we did is we implement a whole program transformation of the annotated program, and we take the console as a transpiler. We take the annotated program and we compile it to the ordinary Solidity programs, which can be directly running on the EVM virtual machine. And there's a translation, a little bit formalization, more details in the paper, but I won't talk too much here. I just want to explain a little bit more about how we implement those things to track addresses. And the basic idea is first we want to change the value representation of addresses because the Zhou addresses, they're just 160 bits integers. And we want to encode additional information about what conditions should be checked when calling what functions on this address. And when the call actually happened, we decode those additional provenance information and decide what are those conditions should be checked actually. Right. So the example here roughly demonstrates the idea. We have originally a function f and it's taking an argument adder and then call adder the g function over adder. And then we translate to change the value representation, which is the type here. It's a guarded address. And then at the beginning of this function, we would attach the subspecification to this guarded address value representation so that later we can use those information. And the call side is also rewritten in the sense that we get a dispatch function taking both the guarded address and the normal argument. And inside of the dispatch function, we will decode the actual provenance information and perform actual check around this value. Right. But now there's a caveat actually. We must be actually careful because we're doing solidity and EVM. And there's a quite different cost model on EVM because all transactions on EVM, they take a transaction fee. And those transaction fee, they are related to how much storage you use in your program. If we're storing more information into those addresses values, we may cause additional transaction fees, which is undue for any users if they want to use this thing in the real business setting, right? So but luckily there's also a trick in the EVM platform. Even though the original address is 160 bits, but for loading and storing those values, less than 256 bits causes roughly the same amount of gases. So we can exploit these things to basically expand the addresses values to 256 bits and use the additional information to encode those subspecifications. Right. Here we can use additional 96 bits to encode the specification. And you can see here, we first expand the row addresses to from 160 bits to 256 bits, and then we can use that higher bits to mark which is precondition and postcondition to be checked. And at a later point at the call site, the dispatch function will read those information and get to know what are the actual checks here. And this actually causes very little overhead, which we will see later in the evaluation section here. So for evaluation, we build a prototype tool, and we want to know two questions basically. The first one is how expressiveness of console is. So especially in the setting to express those security differences. So, and we can also to see to what degree we can decouple those security checks from business logic. And the second question we're interested in is how much overhead is introduced by our console translation. Right. And the first, to answer the first question, we collected around 20 cases from the real-world attack databases, and you can see roughly a summary of those attacks and the total loss of those existing attacks and the root cause of the vulnerability. They cover different varieties, vulnerabilities. Some of them are quite famous, like reentrancy, and some of them probably not, like integer overflow, which is also a common software mistakes here. So the total amount of loss, it's a crazy number, but they already happened here. And our evaluation is compared against those low-level assertion checks, because their attacks already happened and people already patched those programs using just the assertions to specify those critical conditions. And we want to see whether we can use console to simplify the specification of those security checks, right? And the result is pretty good, and we can basically as effective as those low-level assertions, but we can also simplify the program, especially the main business logic, really a lot. And you can see the table on the right here shows the line number reduced from the function. And roughly around almost a half lines of code in those functions being attacked can be extracted to our console specifications. So you don't really need to intertwine those assertions with your main business logic, which improves readability a lot. And the second question is how much overhead is introduced by console translate programs. And for this question, we already have those benchmark programs from those real-world attacks, and because we can only run 16 real-world attacks, and we also collected 23 contract programs from previous paper by Li from the PLDI20. Those are smart contract programs, are pretty standard protocols in the EVM solidity setting. And our baseline, again, is to compare with low-level assertions already patched in those contracts, because those low-level assertions already exist. And if programmers migrate those low-level assertions into our console annotations, we want to know whether they will cause additional overhead. And so this table shows the result we did on those 16 real-world attacks. And you can see the numbers on the right here is the gas, additional gas introduced compared with low-level assertions. And on average, it's just less than around 0.2% of additional gas, which is really a marginal number and doesn't really affect any really business purpose. And for the second benchmarks, we evaluate on those ERC protocols. And again, the result is similar, and we also have around 0.29% of additional gases. So those gases are really good numbers and marginal. So to evaluate those things, we also replay those existing transactions on a simulated blockchain to simulate the real-world setting. Okay. So this is about evaluation. I just want to quickly summarize. We propose this console as an extension and a compiler to Solidity, and the main feature is really this behavior contracts for smart contract. It is much more expressive compared with existing work on smart contracts programs, because we can specify and monitoring conditions for addresses values and their latent costs. And we also have a little bit clever encoding about those values and the spec encodings, which introduce only marginal gas overhead running on the Ethereum platform. So we have a prototype, and also our evaluation data is on GitHub. Thank you for your attention. I'm happy to take questions.
Anyone has a question?
So, very good talk. So if I understand it correctly, so your behavior contract is actually a dynamic check, right?
Right.
So as you said, if you have a bug in your smart contract, you will lose money, and if you have overhead in your dynamics check, and you have some transaction fee, so why don't you not choose some static check, for instance?
Yeah, that's a great question. There are already existing a lot of work on static analysis and static verification of smart contract programs, but not all information you have is available before running on the blockchain. And if you're doing dynamic analysis, you have more information to know what actually happens. And because we're following this behavioral contracts approach, the programmer can write arbitrary functions or computations as specifications. They're executable, but this can go beyond the capability of static analysis sometimes.
Yes, maybe fall to the old question. So who can verify this your behavior contracts?
Only the programmer, or ideally there some business person design this contracts from the business perspective. There are some people implement those things.
Yeah,
and those behavioral contracts should be more close to the actual business contract.
Okay.
I think that's probably the ideal case, but I'm not sure how much that's reflect the reality.
Yeah, okay, thank you.
Yeah. Thank you.
Thank you.